Good evening, students. This is the second lecture of the JAM exam preparation. This video covers three topics, that is Aufbau Principle, Pauli's Exclusion Principle, and Rule of Maximum Multiplicity. What is the use of these three principles? These three principles governs the filling of electrons in the orbitals of an atom. Okay, what is the electronic configuration of atoms? The distribution of electrons into orbitals of an atom is called its electronic configuration. Okay, and consider this is the nucleus, and this is the various energy levels of an atom in which the electrons are revolving around. In the nucleus, there are neutrons and protons. This is the miniature of our solar system. Aufbau principle. The word Aufbau in German means building up. The building up of orbitals means the arrangement of orbitals in increasing energy on the basis of n plus L rule. What is n plus L rule? The sum of n value and L value. Based upon the sum of the n plus L value, the electrons are filled. The principle states in the ground state of the atoms, the orbitals are filled in order of their increasing energies. This is the diagrammatic representation of Aufbau principle, in which you have to write the s orbitals, and in between that you have to write the p orbitals, then the d orbitals, then f orbitals. You have to link like this, the s orbitals and p orbitals like this you have to link. Then how can you write the increasing order of energy levels is 1s, then 2s, then 2p, 3s, then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. The electrons are filling in these orbitals like this, in the increasing order of their energies. In other words, electrons first occupy the lowest energy orbital available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. As you have learnt above, even the energies of the orbitals are affected to different extent by different type of orbitals are affected to different extent. Thus, there is no single ordering of energies of orbitals which will be universally correct for all atoms. Okay, there is some variations for separate atoms. However, following order of energies of the orbitals is extremely useful. The energy order is like this. First, the lowest one is the 1s orbital, and then the 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, like that. It continues. Next principle is Pauli's exclusion principle. The number of electrons to be filled in various orbitals is restricted by the exclusion principle given by the Austrian scientist Wolfgang Pauli in the year 1926. According to this principle, no two electrons in an atom can have the same set of four quantum numbers. Pauli's exclusion principle can also be stated as only two electrons may exist in the same orbital and these electrons must have opposite spin. Okay, according to this principle, no two electrons in an atom can have the same set of four quantum numbers. All the electrons are unique. No all the quantum numbers will be same for 2 electrons. At least it will be differ in the spin quantum number. Otherwise, it easily explained each orbital should have 2 electrons, the electrons with opposite spin. This means that the 2 electrons can have the same value of 3 quantum numbers n, l and ml, but must have the opposite spin quantum number. The restriction imposed by Pauli's exclusion principle on the number of electrons in an orbital helps in calculating the capacity of electrons to be present in any subshell. For example, subshell 1s comprises one orbital and thus the maximum number of electrons present in 1s subshell can be 2. In P, D and F subshells, the maximum number of electrons can be 6 and 10, so on. This can be summed up. Totally, the Pauli's exclusion principle summed up like this. The maximum number of electrons in the shell with principal quantum number L is equal to 2n square. Suppose if the n value is 2, the maximum electrons filled in that particular shell is 2 into 2 square, that is 8. The maximum value of electrons filled in which the n value is equal to 2 is 8. Like that, we can calculate the number of electrons, that is the maximum number of electrons present in any shell. The third one is the Hund's rule of maximum multiplicity. This rule deals with the filling of electrons into the orbitals belonging to the same subshell. Orbitals of equal energy called degenerate orbitals. What is degenerate orbitals? Orbitals of equal energy. Orbitals of equal energy is called degenerate orbitals. For example, this is p orbital, this is px, py, pz. All these orbitals are called as degenerate orbitals. It states pairing of electrons in the orbital belonging to the same subshell p, d or f does not take place until each orbital belonging to that subshell has got one electron each. That is, it is singly occupied. Since there are 3p, 5d, there are 3p, 5d and 7f orbitals. Therefore, the pairing of electrons will start in the p, d and f orbitals with the entry of 4th, 6th and 8th electron respectively. How? This is p orbitals and the pairing is 1, 2, 3. In the 4th electron will come and pair. All the alkali metals with the electronic configuration in its outermost shell is NS1. For lithium it is 2s1, for sodium it is 3s1, potassium 4s1, rubidium 5s1, cesium 6s1, francium 7s1. Okay, this is the additional topic for the JAM examination preparation. Elements are classified into metals, non-metals and metalloids. And the periodic table classifies the elements in several ways. You have already learned about the S, P, D and F block elements. In this article, we will discuss another broad classification of elements, metals and non-metals. The classification is largely based on the chemical properties which are common among the divisions. We will also talk about the third category of elements called the metalloids. Okay, in this slides, we are going to discuss about the properties of metals, non-metals and metalloids. First, the metals. 78% of known elements are metals. They take up the left side of the periodic table. At room temperature, they are usually solids, except mercury. They are usually have high melting and boiling points. They are shiny, having a metallic luster. They are good conductors of heat and electricity. They are malleable, that is, they can be hammered into thin sheets. They are ductile, that is, they can be drawn into wires. All the metals tend to lose electrons easily. Therefore, all the metals are good conductors of electricity and heat. Non-metals. Let us see about the properties of non-metals. They occupy the right-hand side of the periodic table. Most non-metals are brittle and are not malleable or ductile. At room temperature, they are usually solids or gases. Usually, the non-metals having the properties just opposite to the metals. They usually have low boiling and melting points, except for carbon and boron. They are poor conductors of heat and electricity. They are usually less dense when compared to metals. They tend to gain electrons during chemical reactions. Then metallites. Metallites exhibit some properties of metals as well as non-metals. Hence, they are also known as semi-metals. Boron, silicon, germanium, arsenic, antimony and tellurium are the most commonly recognized metallites. These elements run diagonally across the periodic table. They may have a metallic or dull appearance. They are usually brittle and are fair conductors of electricity. They may gain or lose electrons during chemical reactions. They form alloys with metals. They are used as catalysts, biological agents, flame retardants, alloys, and semiconductors in industries due to their unique properties. That's all. That's all, my dear students, about the second lecture of the JAM exam preparation. In the coming lecture, we will discuss about the periodic properties of elements in the periodic table. Okay.